Okay, hi everybody. It's always a pleasure to be back. And let me just say, as a caveat, that this is like a pretty new result, which we put up in the archive, Aaron Landsman and I, a couple of weeks ago. So this is the first seminar talk I've given about it, and I've been like constantly changing my mind about what order to say things in, and I'll only figure it out by like giving the talk. So feel free to tell me if you think I should have said things in a different order from the way I'm going to say. And actually, Akshay said there was going to be like a mix, and there was going to be some theorists here and some topologists here, and I'm wondering if that's true. Like, are there who's a topologist? I know you, Greg. Who's a topologist? Okay, so not so many, mostly number theory crowd, because that's sort of relevant to sort of how I say things. So I want to talk today about a new result about, so first of all, let me emphasize that everything I'll say today is joint with Aaron Landsman. I'm going to talk about a result about Selmer groups of abelian varieties and families of quadratic twists. But it's sort of part of a general program, which also has relations to what you're going to hear about from Craig and Dan like later in the week. So this talk, I'll also mean it to be kind of like an introduction to that program for people who aren't familiar with it. So I think what I'm going to do is start with what we actually prove, and then I'll sort of say a little bit about the sort of general strategy. I'm going to say very little about the details of what's actually in this paper, because the interesting parts of that are in some sense like pretty deep into the technical guts of what happens. So, okay, the title, Selmer groups in quadratic twist families of abelian varieties for function fields, and it's a kind of a woven reminder of like what kind of thing this is. So if K is a global field, which much of the time is a number field, but for today is basically always going to be the function field of a curve or a finite field. So A, an abelian variety over K, and of course, the thing we study all the time is the Mordell-Weil group of rational points of this abelian variety, which is some finitely generated group. So some z to some power plus some portion group, which we're certainly not going to think about so much today. And this rank is, of course, one of the most fundamental variants of an abelian variety. And in some sense, the main way that we have of studying it is this proxy, which is somehow easier to get at, which is more sort of a little bit less geometric and more number theoretic in nature, called the Selmer group. And I think I'm not even going to recall the definition, because if you know it, you know it. And if you're a topologist and don't care about it, it's not so relevant what the definition is for today's talk. I'll say a little bit about what it is as we go. But so cell LOA is a particular finite group. Maybe I will at least say that it sits inside a Galois cohomology group of H1 of GK on the L torsion of A. It's a finite group, and it's actually like a finite dimensional space over Z mod LZ, and its dimension is an upper bound for R. That's sort of fundamentally why we care about it. So we might call it Z mod LZ to the RL. Oh, I guess I was noticing in Maria's talk, if I write here, all of you guys can't see it, right? Because I was sitting over in that seat earlier. Okay, so maybe I'm going to try to not write any more like over in this part. And the point is that R is less than or equal to RL. So this Selmer rank is an upper bound for the honest rank, and that's one reason we care about it. And so the question is just like, so it would be great if this were like always small, right? Because that would tell us the rank were small. So a question is, what do we expect this group to look like? It's an invariant of an abelian variety, just given by a single number, because there's not so many vector spaces over a finite field. And there's a wonderful conjecture of Bjorn, Poonen, and Eric Rains, and then followed up by a more general conjecture where we add some more people. Let's see, did I write down years for this? I think this is 2013 and this is 2015 or something, but around that vintage. Which suggests that heuristics for, sometimes I'll call this a mod L Selmer group, of a random elliptic curve. Now, what do I mean by a random elliptic curve? I'm going to be pretty vague about that because in some sense, there's lots of different models of what I might mean by a random elliptic curve. And I suppose rather than trying to pin this down, we could say for which of those notions of random is the heuristic I'm about to lay down correct. So when I say heuristics, I mean there's actually literally a proposed probability distribution of how often you're supposed to get each possible rank. I can write down for you, but I'm not going to do it. I just want to sort of tell you some things about it. Which predict, for instance, that the average size of cell LE, it gives a precise value, L plus 1.
Your size means finality, not dimension.
Yes, absolutely right. So the average, it's the average of L to the RL. Thank you. Yes. So maybe I'll say a couple of things about that. One very elementary, and then one from a sort of geometric point of view. So if the average, I mean, remember, as Nick pointed out, this is the average of a probability distribution on integers, which are all powers of L. So if the average is L plus 1, it's pretty hard for it to be a big power of L, right? And in particular, the probability that you're L squared or greater, it better be pretty low, right? That's not going to be like a half or something, because then you would get like a constant times L squared. So in particular, the probability that this rank is greater than or equal to 2, I mean, there's some sort of like long infinite product, but it's on order L to the negative 1, as it kind of has to be, or else its expected value would be too big. So one thing you should think of this as predicting is that it's quite rare for the Selmer rank to be 2 or bigger. And in fact, it also predicts that it's sort of 50-50 between, the leading term for 0 and 1 are both 1/2. But what I want you to note is that, remember, the honest Mordell Ray rank of this thing is bounded above by RL. And I didn't say which L I meant, like this is true for every L. So you should think of this as saying, whence, if you believe these heuristics, we should expect the probability that the rank itself is greater than or equal to 2 should be 0, because you sort of pick some very large L. If you believe that it's rare even for the L Selmer rank to be bigger than 2, then all the more so you believe that for Mordell Ray rank, and this can be as small as you want. So this kind of is in keeping with this philosophy, which I guess goes back to Goldfeld, that we should expect high rank, where high means 2 or bigger, to be quite rare. Maybe I'll say one more thing about this, and I'm going to kind of mix like how much I say from topology and how much I say from algebraic geometry in this talk. So, I mean, why would we get this? And in particular, like, where do these heuristics come from? I want to say one word about that. One way to think of this is think of an elliptic curve, remember one version, I mean, this conjecture is actually, I'm not even sure if I don't even remember which one of these papers are stated for general global fields. I mean, people usually think of them like over number fields, but if I do think of an elliptic curve over the function field of a curve, as an elliptic surface, I sort of spread it out to be like some kind of surface over C whose fiber is an elliptic curve. And it turns out that you can really think of this, in this case, what the Selmer group actually is all right, so let me put big scary quotation marks around is, because like this quotation is means like basically is related to by some stuff that I'm not going to write down, but is about the same size. Frobenius fixed part of H2 of this surface, the atomic homology of this surface with coefficients in Z mod LZ. Okay, so what is that? Well, Frobenius acts on this H2. This is H2 of a surface. So that Frobenius is going to act like an orthogonal matrix, right? There's a pairing on that H2, and because 2 is even, that pairing is orthogonal.
This is geometric H2.
This is H2 of E, this surface over FQ bar. Absolutely. So it's just the geometric H2. Thanks. A space on which Frobenius acts as an orthogonal matrix. And so, yeah, I mean, this is sort of what I learned from Nick when I first came here as a postdoc in like 1998 or whatever it was, that when we have Frobenius acting and all we know about it is like what kind of group it sits in, we just sort of should pretend it's a random element of that group and like see what happens. And so one way of thinking about where these heuristics come from, well, this is not exactly the way that Bjorn and Eric think of it, is what if Frobenius were just a random orthogonal matrix? And then you could sort of play a game. I take a large dimensional vector space over Z mod LZ, and I choose at random an orthogonal matrix in there. And I ask, what's the dimension of its fixed space? So it's a fun exercise to say, so check if gamma is chosen at random from some gigantic orthogonal group over Z mod LZ, then the expected size of, let's say, of the kernel of omega minus 1 is exactly L plus 1. And any other statistic you wanted, essentially the Poonen-Rains heuristic that says that it agrees with the statistics of a random orthogonal matrix. I mean, this is kind of a fun story, actually. And why is that? You guys know Burnside's lemma, right? The sort of the expected number of fixed points of a random element of a group acting on a finite set is just the number of orbits. So really the reason it's L plus 1, if you want to know where that comes from, is that if I think about the orbits of your orthogonal group on a large dimensional vector space, well, two vectors are related almost, if and only if they have the same length. And there's L possible lengths. The only difference is there's two kinds of vectors of length 0, right? There's 0, and there's all the other guys of length 0. And so that's why it's L plus 1 instead of L. Okay. So maybe what I'll do now, having sort of said what kind of expectation this is, maybe I'll actually say the theorem. So this is the theorem. And I'm not going to sort of try to state the theorem in full. I'm going to sort of state a consequence of it that gives the idea from this paper we just posted a couple of weeks ago. Let's let C a curve over some finite field. Let's let E be an elliptic curve over that function field. And let's let all right, what's my notation be here? So F, because after all, if I'm going to state a theorem, I actually now do have to tell you something about what I mean by a random elliptic curve, like which one I'm picking. So F chosen at random, actually, maybe I'm going to make my life a little bit simpler to state by taking this to be a rational function field. So let me make this over F cubed. F chosen it to, just so I can say square-free polynomials here instead of square-free divisors, and there'll be some other stuff I want to be a little careful about. So F chosen at random from square-free polynomials of degree n, and then by E sub F, I mean quadratic twist of E by F. Okay, so now I have an actual model for something I might mean by a random elliptic curve. And this is certainly not every elliptic curve. I've started with a particular one. I'm going to take some quadratic twists chosen at random from quadratic twists of very large degree. But this is certainly a way of making large height elliptic curves in large numbers. And then what we'll show is that then the expected value of the size of the L Selmer group of E twisted by F. So now, like, I have a random variable, so it has an expectation. This is what I want to be L plus 1. And we don't quite prove that, but we prove something close. Well, first of all, this is supposed to be true as n goes to infinity, right? I mean, as we take like larger and larger twists. So what I'd like to write here is a limit as n goes to infinity. We don't quite know that exists, but we do know there's a lim sup, and that's, again, so the existence of this lim sup is certainly not obvious. It's not obvious that this would be bounded in expectation as n gets larger and larger, but it is. Can we say that it's equal to L plus 1? Like, not quite, but it's something which is finite, and as the field we're over gets larger and larger, it gets closer and closer to L plus 1. So let's say the limit is Q goes to infinity, and depending how I set this up, I could set this up in such a way that Q is actually allowed to change characteristics. But let's say for the moment, just so I can state something that's easy to say, that this Q goes to infinity means E starts over FQ, and then I'm passing through larger and larger extensions of this finite field. So it's really going through, maybe I should say Q to the J goes to infinity. Well, you guys know what I mean. I'm just like replacing Q with powers of Q. And then this limit actually equals L plus 1. And then the same is true for limits. So this is bounded above and below by things which the larger Q is, the closer those upper and lower bounds are to L plus 1, the Poonen-Rains expectation.
So, Jordan, you don't actually mean that curve C anymore, right? Because you right?
Oh yeah, sorry, I wrote it and then I thought better of it. So, but I mean, I will say I'll put it in parentheses because I'll comment that if you look at the theorem statement, there actually, you just have to be more careful about phrasing it. There's a statement that holds for not just elliptic curves, but abelian varieties of whatever dimension, and over an arbitrary function field. It just makes it a little harder to state. But I forgot a condition, so I'm glad you asked me to look at the theorem statement again, because we do need this to has at least one place of multiplicative reduction. So for instance, if you were to try to do this with a constant elliptic curve or even an isotrivial elliptic curve, those heuristics might look a little bit different. That's actually sort of more like the Cohen-Lenstra case that Akshay and Craig and I wrote about in our earlier paper using this kind of method.
You have similar results for the L power.
Yeah, so again, sorry, I'm trying to write this as compactly as possible, but in fact, in the paper, it can just be like an arbitrary integer. So it can have different L's in it and like everything is, so you sort of get independence between different primes and everything. So, but it's good, by the way, to write papers with young people who are like to do everything in like maximal generality, because I get very tired. And then like, do we have to do it for all the powers? Like, yes. Do we have to do it for all the composites? Yes. But then it's better, right? It's better not to like leave that work for like someone else to do. So yes, it's
Sounds like you are leaving it for someone else.
So I'll just comment that there's like a large body of work about sort of like about results towards Poonen-Rains and like, some of it by people in this room. So I'll just comment that in some sense, like what we know about ranks and families of elliptic curves largely comes from what we know about Selmer groups for various mod L Selmer groups for various L, or mod N Selmer groups for various N. And so I'll just comment that because, and the better and the bigger the L, the stronger the results on rank, sort of for that reason that I showed you here. So the fact that this is true for all L means that you can actually use it to show that in a family of quadratic twists, you can get the probability of having rank higher than 2 to be quite small. And again, the nature is sort of just like this. You can get a proportion of rank greater than 2, which is sort of bounded by something, not 0, that would be cool, we can't do that, but some function of Q which shrinks as Q grows.
I mean, the factor down, 1 over Q or?
It's okay. Let's see if I can say this right. I think it's more like 1 over root Q, but I don't know. It can be made effect. I mean, it can be made explicit. Yeah. I think
1 over root Q is better than explicit.
Yeah, it's better than some explicit things and worse than other explicit things. I don't know. Yeah, so but it can be made explicit. Okay, so what do I want to say? I think now, okay, so I've used sort of 25 minutes to like lay out the sort of main thing. Now let me sort of say something about the general philosophy that this is part of. So it's going to seem like I'm sort of making a somewhat wrenching change from what I've been talking about, but it's really the same. So, how do we approach problems like this? Using topology, because in the end, the sort of fundamental argument here is a topological one, and I want to sort of explain like how you get there. And it's a question that doesn't really look like it's about topology at all. So let me start with a question that's going to appear to be rather different. So question: let D, actually let's let G a finite group, and let G be a random square-free divisor on the affine line over FQ. So I guess I just said again, a random square-free polynomial. I don't know why my notes, I choose to say it more pretentiously this time, but it's like the same thing, right? I mean, I'm picking some random square free polynomial. And now we can ask a question. How many G extensions of this function field are there with, well, let's say, unramified outside D. So, I mean, this problem of like counting extensions with a fixed Galois group and specified discriminant, I mean, this is sort of the first stuff that actually I worked on together, actually, when actually I was a grad student. I was in the middle of my postdoc here. And this question, which seems like it's sort of somehow a question in algebraic number theory, right? It's a question about extensions of global fields, a question in, so to speak, arithmetic statistics. In the function field case, this becomes a geometric question. That's what I want to explain.
Should you say anything about ramification and infinity?
Okay, so one thing we could do is be careful about specifying what ramification we have at infinity, and I've decided to be careless about that for the purpose of this talk. But like, if we were like, we could specify it, but I think everything I'm going to say right now, I don't need to specify it. However, thank you for reminding me, because I do want to comment. We might want to further specify. What if we specify that the ramification at points of D is of type, and now I'll use notation little c, where I'm just referring to some conjugacy class in G, right? Because this cover may be branched at D, and I may want to keep track of what the monodromy is there. So if you don't think about this kind of problem, so a running example to keep in mind is, e.g., maybe I'll look at the sort of the generic case, like extensions whose Galois group is the symmetric group, and then I require that these covers be simply branched, which is the sort of typical thing we do in algebraic geometry. And that means that when I sort of make a little loop around this ramification point of the base, just two of the D sheets come together. So the conjugacy class in SD would just be the conjugacy class of a transposition. And that's already a very rich question. In fact, this question is the sort of classical notion used by Hurwitz to prove that the moduli space of curves is connected. And so all of these guys, sort of in deference to that story, are called Hurwitz spaces. And that's sort of the fundamental object of study. I got a little bit ahead of myself because I didn't say where there was a space yet. Sorry, I'll say that now. So
D doesn't factor completely. It means each irreducible factor of D. I mean, D is an irreducible polynomial.
yeah, so I guess I mean for each closed point of D, like so right, if it was irreducible, there would just be one big fat closed point with a big residue field, and there would be like, and then it would be automatic that there's just sort of like one way that the ramification looks, and you want it to be this. But if there was like a bunch of closed points, there's more conditions. In fact, if I fix D, already it's not hard to check that there's like only finitely many of these. And so I want to think of it like this. So let's use this notation. By conf n, I just mean the space of square free degree n divisors on A1, which you can also think of it as the space of, I mean, this is why it's called that, configurations of, geometrically speaking, it's configurations unordered of n points on A1. So you can either think of the square free polynomial, or you could think of its n roots, which are endpoints that don't come in any particular order. So that's like a very natural moduli space that parameterizes square-free divisors. And for each one of these, for each such D, you have some finite set of G extensions, which are ramified at those endpoints. So the picture you should have in mind is some finite cover where we'll call her GNC, and it maps to comp N. This is called a Hurwitz space. This is configuration space. Let's call this pi. And then our square-free divisor is a point on here. And then pi inverse D is the set of G covers ramified with the ramification of type C at D. So for any question of this kind, if I want to know, I said how many, but maybe I mean if I choose D at random, how many are there of these on average? That comes down to saying how many rational points are there in an average fiber, in a randomly chosen fiber of this map. And so the answer to that question, average number of G extensions for a random D is really nothing other than the number of points on the big space divided by the number of points on the lower space. That's by definition the average number of rational points on the fiber. And this is something that we know. I mean, I could say exactly what it is. It's like 1 minus 1 over q times q to the n. So we're going to ignore this as like basically q to the n. So really the question is, how can we, so we've turned it into a problem of algebraic geometry. How can we count rational points on this space? So maybe I should say one thing here to pause from this discussion, because I'm a little worried I won't say anything else about this particular paper. And so maybe I'll just take a brief aside to comment that it seems I have switched to talking about a totally different problem, a problem that you may have heard me or Akshay or Craig talk about before, this problem of counting G extensions with a given discriminant. One key insight of this paper, which really came out of Aaron's thesis, is that actually this problem of average Selmer is of this form. So even though it seems like I'm talking about a different problem, sort of like one of the key moves in this paper is to sort of translate this problem of Poonen-Rains into a sort of yet another Hurwitz space counting problem. So let me just sort of comment over here on this page of how that works. So remark, so let me ask you to recall that this Selmer group of, and just for the heck of it, maybe I'll sort of write for an abelian variety, is a subgroup of this Galois cohomology group of Galois on the L torsion of A. But this can also be written as just, you know, like x1 of Z mod LZ on AL, I guess in the category of JK modules. And so we could think of it as, I mean, what's an extension of AL by Z mod LZ? It's kind of like a thing that looks like this. So there's like an AL here, and there's a 1, and then there's some stuff. So what it really is it's a Galois representation, but not an irreducible one. It's one that sort of has like, I hope I wrote the subrep and the quotient in the right place. If I didn't, I wrote it wrong. Okay, everybody transpose this matrix I just wrote down. Sorry, this is like I'm going off notes here. Can I fix it by just writing asterisks here, or is that not going to do it? Okay, good. Okay, or just turn your head 90 degrees if you already wrote this in your notes. So anyway, the point is that this is basically given by certain kinds of homomorphisms from Galois to what you might call the affine symplectic group of 2G by 2G matrices over Z mod LZ. So this is 2G by 2G, where G is the dimension of the abelian variety. And then there's a group of matrices that look like this. Like it's a semi-direct product of this symplectic group by a Z mod LZ to the 2G that it acts on. And so this is an extension of K with Galois group a certain group. And it turns out very nicely that, I mean, if you know Selmer groups, you know, like, well, wait a minute, it's not just like an element of that Galois cohomology. There's these kind of funny local conditions at the bad places that you have to be very careful about. And it turns out that in this case, under mild conditions, which are all of the form, they're not so scary, right? They're like, okay, the bad places, I don't want L to divide the group of like their own components ever. They're all things that are sort of like annoying, but which are going to be true for almost all L. So under hypotheses like that, these Selmer conditions, basically just become monodromy conditions of like which conjugacy classes you're allowed to hit. So it turns out that you really can express this whole problem as a Hurwitz-based problem. That being said, you know, you may know that the first paper I wrote in this area, which is my work with Craig and Akshay, it proves some theorems about certain kinds of Hurwitz spaces where you can control the number of rational points. But this group is definitely not allowed in that paper. And so in some sense, some of the novelty in this paper is how we get around that. But that's technical and boring unless you really know how that original paper works. So I just want to say there's sort of something going on here where we sort of like get past some technical thing that we thought was like a real wall and turned out not to be. But I'm not going to talk about it in this talk. But so I think for the rest of the time, I'm really going to sort of say a little bit more about this general story of like what's the, because I haven't gotten to topology yet, and I'm going to do it before the end of the talk for the topologists who are here. Okay. So the fundamental tool, right, we're sort of trying to compute the number of FQ rational points on some space, and the fundamental tool for doing that is the Grothendieck-Lefschetz trace formula, which allows me to express this number as an alternating sum from I equals 0 to this is an n-dimensional space, so we're going up to 2n. It's an alternating sum of the trace of Frobenius acting on, uh-oh, I'm doing that thing again where I'm not supposed to write over here.
We can still see it.
Okay. And then it's just the coefficients. You don't care what the coefficients are. They're QL bar, but nobody needs to know that they're QL bar. Okay. And this is again the geometric H1. Okay. So as always at this part of the talk, right? It's like I took something that sounded kind of nice, like counting points on a space over a finite field. I'm like, oh, now all you have to do is like do this like impossible thing of like understanding like all the atomic cohomology of some crazy space that we know nothing about. So I'm going to take the rest of my time just to sort of explain the sort of topology of what kind of stuff we might know about this space that allows us to say something here, because there's a lot of different problems by now in this vein, including the work that Craig and Dan are going to talk about. And I want to sort of give some kind of a blueprint for what information about homology translates into what kind of results on counting. So, before I do that, I definitely want to make sure I sort of bring this down to topology, so I'm going to do that first. Okay, so, because this still doesn't look like topology yet, right? This still looks like atomic cohomology of some space over a finite field. So let me just say, I'll just say wonderfully, to say that I'm not going to explain it. it turns out that these moduli spaces are nice enough that we can actually compare their atomic homology over the finite field with their homology and characteristic 0. And we get very lucky, and in some sense, there's reason, I mean, this particular class of things has worked very well for this. So wonderfully, we can, well, of course, the Frobenius action is lost. But we can at least compute Betty numbers. We can at least compute dimensions of spaces. We can compute the dimensions of these spaces over C. So we can get away with just computing the HI of now this Hurwitz space over the complex numbers, and just, with rational coefficients, or whatever.
First one is compact homology. Does that matter?
So it doesn't matter, but here, right? So I'm sort of Poincaréing this over, but right in the formula it should be compact homology, but I'm just switching the sides, and it doesn't matter for this.
Is the space is smooth?
Yeah, all these spaces are smooth, absolutely. So I'm that allows me to be lazy about that issue. So
you need Q for the dimension.
where? Up. Where do I need it? Oh, you mean when I Poincaré dual it over to here?
No.
Yeah, so maybe I should say okay, I'll mess it up before I try to say it. Well, what if I just write the C here so I'm telling the truth, and then we can compute it in terms of this? The problem comes down to just compute, at least the problem of computing the Betty numbers comes down to computing the topological homology of these guys. So again, I mean, when I just talked about this space, notice that here I actually never said FQ. See, I was thinking ahead, like this whole page makes total sense if I think about configurations of endpoints on C, on A1 of C, and square free divisors on the complex affine line. But now this configuration space is one that topologists know very well, right? Because the complex plane is like a disk, and the configuration of n space is endpoints on a disk. So note that comp n of C is a k pi 1 for its fundamental group, which is just the arc and break group on n strands. So, I mean, one of whose definitions is just that it's the fundamental group of endpoints on a disk. The braids are the way endpoints can move around each other on a disk. So if I have a finite cover of a space which is a k pi 1, this is completely described just by an action of that fundamental group on this finite set. So there's a purely combinatorial description, which I'll now tell you what it is. And her GNC corresponds to an action of the braid group on the following finite set. Ready? I just take this conjugacy class, which is a finite subgroup of the group, and I just raise it to the n. So it's acting on n tuples of elements from that conjugacy class. Okay, so I can't resist. I mean, if you haven't seen this, I'll just sort of say, what is this mysterious action? It's just like a braid that looks like this and pulls strand I plus strand I plus 1. It sends this n tuple to, okay, I'm again going off my notes. So like the transpose matrix, I'll either write something that's true or like a thing that you can make true by mildly changing it. Let's see. So CI inverse, CI plus 1, CI, no. It's the other way. Good, okay. So I sort of pull one back and I pull this one forward, but I conjugate it, but it's still in the conjugacy class. That's still an n tuple of conjugacy classes. And this so-called Hurwitz action is the finite set we're acting on. So to sum up, when I compute the cohomology of this space, which is a finite cover, so HI of the complex Hurwitz space is the same thing as HI of the braid group in the permutation representation on this set. So I guess I'll write it as the space spanned by n tuples. So this is a pretty big space, right? I mean, its dimension is the size of C raised to the nth power. But to write it another way, I can just think of it as the space spanned by the conjugacy class tensor with itself to the nth power. Same thing, right? I mean, like the space spanned by the n tuples of things drawn from C is the nth tensor power of the space spanned by the elements of C itself. And I write this to be like a little bit provocative because this should look pretty familiar, right? If I have some vector space and its nth tensor power carries an action to the braid group, that's probably because it's like what's called a braided vector space, right? So this is sort of an
I'm a little confused now because
cool.
when we're in the F2 world, we have a conjugacy class for each irreducible factor for polynomial D. And this seems to only be relevant to polynomials of factor completely.
Okay, great point. So I feel like I was probably unclear. What I meant to specify by like writing this little superscript C everywhere is that I wake up in the morning and I pick that conjugacy class, and then at every irreducible factor of D, it's required to be like the same conjugacy class. So there's only one conjugacy class that's ever allowed to be used. Now here, since I'm over the complex numbers, there's no issue of there's no issue of Galois conjugacy. I mean, the discriminant factors completely because it's over C. But yes, I should have said like there's always just one conjugacy class that's the monotomy everywhere. You don't like that? It's like with simple branching. When you say cover is simply branched, you mean like everywhere it's ramified. It just switches two sheets and doesn't do anything else. Okay. I mean, there are versions of this where we could allow different kinds of ramification at different points, but then it's more complicated. You have multicolored configuration spaces, and I don't want to discuss it. So I just mean to say that this now is something I would call, would we even call it topology, or would we just call it group theory? I don't know what we'd call it. Do you think it's topology, Craig? To like,
I mean, it's homological algebra. It sounds like
okay.
topology.
So I'll just sort of close by saying that somehow in this whole family of problems, somehow we always end up doing, can I say all? So in general, in many different problems, we find at the end, we need to compute or at least bound, which in many cases is the best we can do for the moment, the cohomology of the braid group on n strands in some coefficient module which varies with n. And this is going to be my transition to Craig's talk. And so now you're like, okay, so what are the sequences of representations of the braid group? Where for each n-strand braid group, you have a different representation. There's sort of a bunch of different kinds. So let me sort of close with a little table of different families of representations of braid groups and what arithmetic problems they correspond to. So e.g., let me get my table so I get it right. Okay, so arithmetic statistics problem. The space we're studying and the cohomology we're computing. So the sort of basics example is if we study the configuration space itself. So counterpoint configuration space itself is like, well, this is a K prime 1 for the Bray group. So this is just like the trivial representation. This is just like computing the cohomology of the Bray group with constant coefficients. And this is what Arnold did long ago. Well, maybe I should say with Q. Craig knows it's a lot harder in characteristic too, but maybe I should say, for the sake of this discussion, Q. So in fact, like, this is almost all 0. There's just like a class in dimension 0 and a class in dimension 1. It doesn't really matter what n is, and that's why this space is pretty easy to count points on. Oh, let's see. Like, I feel like I made this too. What am I going to do? I need this to line up. So I have to move this down. I could have done that, but it was too late. I'm good. Okay. So this is counting square-free polynomials. Okay, because Peter's here, I have to average the Mobius function. I can't give a talk in front of Peter without averaging Mobius at some point. So the average of mu f over square-free polynomials, we know what it is. It's 0, right? It has to be 0. But how is that reflected geometrically? So this space is, the relevant space is some double cover of comp n, and the cohomology is the cohomology of the Bray group in a certain one-dimensional representation by the sign of permutation of strands. So it's a pretty simple representation of the Bray group, because the Bray group maps to Sn by how it permutes the strands, and then Sn has a sign rep to plus or minus 1. And so this is like, I mean, this really is like the same representation for each n. And in fact, this cohomology is all 0, and that's sort of why that average is all 0. Okay, how about average number of points of FQ points on a hyperelliptic curve. So I can get a hyperelliptic curve by choosing a square-free polynomial at random and saying y squared equals that. That's, I mean, that's so my model for a random hyperelliptic curve is very much like my model for a random square-free polynomial. So this space is a space I might call, okay, if HG were the moduli space of hyperelliptic curves, this is HG comma 1. So it's the moduli space of hyperelliptic curves with a marked point. If I count points on that space, I'm sort of adding up the number of rational points on each hyperelliptic curve. And that, so if somebody were like name a sequence of representations of the Bray group, the first one you would probably come up with is the Burau representation. And that turns out to be exactly what homology you're computing. And this was worked out. Who should I say, Craig? Wei An, Chen, and then sort of, I should also write Randall Williams and Vol here? Or is this just Wei An? It's just Wei An. Okay. Okay. Or, okay, maybe I'll write the rest over here.
So when you say they did it, does it mean they computed the stable cohomology or old cohomology?
So maybe you should say a word about where the main term's coming from the right-hand side of your Lefschetz formula in different case.
Oh, yeah. So one big
n go to infinity, Q is fixed, right?
Yes. So I think what I'm gonna run out of time and not be able to do is really explain how these bounds translate into counting. So, maybe
just in the paper that you put 2 weeks ago, which cohomology group is it?
Okay, so maybe I'll just sort of say this in words. The goal is always to show that the H0 is doing all the work. And the H0 is something we have a chance to understand very directly, because of course the H0 of a space is given by its number of irreducible components. And maybe if you want to be over FQ, and how they're defined over FQ. So actually, I'm glad you asked that, Peter, because, since we were talking about when I first came here and the stuff that you and Nick were doing about monodromy, controlling the H0 comes down to a monodromy computation, and absolutely key to the result I'm sort of done talking about, but the new theorem with Aaron is showing that this monodromy group attached to this family of Selmer elements really is big in the orthogonal group, and that uses what Nick did, and it also uses what Chris Hall did when he was a grad student here, also when I first came here. So thank you for making me remember to say that, because that's relevant. So yes.
I guess I'm trying to distinguish between the case that the simplest case where all the cohomology groups except that one was 0, maybe one more, and where there are many cohomology groups, which is where obviously the stable stuff comes in here.
Yeah, so it's in some sense, and again, I'm going to sort of say this quickly because we're at the end, you have this big sum, and to the extent that we can solve these topological or homological algebra problems and maybe control these Benny numbers, we use that to give us upper bounds on the contribution of all these terms other than the H0. Upper bounds by abelian bounds. I mean, because we don't really know anything about the Galois representations. We don't know how Frobenius acts, but we have an upper bound on how big it can be, which gets better and better as I gets larger. So, so that's kind of what's going on.
What sort of bounds do you get on the Benny numbers?
Okay, so maybe rather than continue this list, because this gives, okay, so for more on this and its tensor powers, except now this wasn't solved by this, you'll hear more about this cohomology tomorrow. So what do you want to know about Benny numbers? This is actually a good place to stop rather than continuing this list. And I would say, roughly speaking, there's sort of 3 tiers of things, or maybe I'll just write 2 of the tiers. So you could know that the dimension of HI of the Bray group with coefficients in whatever representation is bounded by some constant times some other constant to the I. And you're like, well, what about n? Well, that's the point. What you would like is some bound on this that doesn't actually depend on n. And that's sort of exactly the quality of the bounds that that Akshay and Craig and I get in our paper on Cohen-Lenstra, and it's very similar, the quality of the bounds that we get in this new paper on Selmer group. And that will lead to situations like the theorem that I stated, where for a fixed Q, at least as long as that Q is large enough, you can get that some limit, well, maybe the limit doesn't exist, but there's a lim sup and a lim inf, and they're close to the thing you want, and the bigger Q is, the closer they're gonna be. Now, what you really want is actually to compute that limit and say that those heuristics are actually correct on the node, not just like more and more correct for larger and larger Q. So this is like in my paper with Akshay and Craig, and then in the new paper with Landesman. So this is good, but better would be to actually compute the dimensions of these things on the nodes, what they are stably, and I mean, ideally, the Frobenius action on them. The best way to compute the Frobenius action is if you can prove that there's 0, then you definitely know how Frobenius acts on them. So I'll just say it's better. So actually compute these dimensions in a range, not just bound them. So best of all, show they're 0. So if we could do that in the case of Selmer, we would actually get that Poonen-Rains was correct for a fixed Q on the nose. And in cases like this, or even with this tensor with an arbitrary Schur functor, you're going to learn tomorrow that the stable cohomology can actually be computed on the nose, and so they get like exact limits, which is pretty cool. Something that for the moment seems quite out of reach for these Hurwitz type problems. Okay, so I'll stop there. Thank you guys so much for coming.
Okay, thanks.
See you again.
In action? No, blogging. Any question? Comments, questions?
Do you really think you'll actually, like, that they're actually zero, or do you think when you fix Q, there should be some discrepancy?
I do think this, I do kind of think the stable ones are zero. I mean, partly because I mean, I feel like these Poonen-Rains heuristics and Cohen-Lenstra conjectures are at this point like pretty well attested. Like in every case where for some sort of reason, like using methods that like Wei knows much better than me, like in any case where you can actually compute something, they're correct on the nose, they're not like off by something. So I guess I've kind of over the years come to believe that.
Can you collect, is this something that you can do numerical evidence for, or is? I think in this case, like we're fixing Q is free.
I mean, you can, but there's real questions about how convincing.
Has someone done it?
I don't know. I don't know if people have really done a lot of numerical investigation of Poonen-Rains. Of Cohen-Lenstra, there's lots of numerical evidence, but for Poonen-Rains, I don't really know. And especially, I mean, again, I should say that, you know, Bjorn and Eric sort of asked their question for, you know, for any family. So these quadratic twist families are maybe like not as much studied. They're probably easier to compute with, actually. I don't know, Craig, you believe that the stable cohomology is zero, right? Uh-oh. So
It's changing some from time to time.
okay. I guess I'll say I definitely believe it for the Hurwitz spaces for Cohen-Lenstra because I've thought about that much more. Maybe I've thought about this new thing like a little bit like less, so maybe I'm like less confident. Yeah.
Can you say a little bit more about how to get this done?
Yeah, so what happens is there's sort of two parts. There's you need a very crude bound that says you have a bound that's exponential in n. And even that, there's cases where that's hard, but in the cases we're discussing here, you can actually just like physically make like a triangulation of the space itself, which has only exponential in n pieces. And so you sort of get this and then the hard part is you need, and I didn't even like really say this word in this talk, but you need a theory of homological stabilization that says that if I is fixed and n is growing, eventually these homology groups stop changing. That's when we say like homological stability. And sort of what that means is that even if n is really big, if it's much bigger than I, it doesn't matter. It sort of stops growing when n is like, 1 million I or something. And then you replace this n with a 1 million I, and then that's this. So it's kind of crude statement, which if you don't have this, you're just stuck at the beginning and you don't know anything. That's the situation for like mg, for instance, where there's homological stability, but you don't have this part. So we still, to this day, can't say anything about the number of FQ rational points on mg. Combined with a homological stability statement, which is usually the hard part, like gives you something, a bound of this kind. And then actually computing the stable homology, which is what we'll see tomorrow, kind of gives us this.
So how does the range affect anything? Because you said that you actually want to compute that in some sort of range.
Yeah, so the reason you need to be careful about the range is because you want to say what's outside the range doesn't matter. And so for that, you want, obviously, the bigger the stable range is, the better chance you have of what's outside the range not mattering. And essentially what's going to happen is that the bigger I gets, the more the Wedelin bounds help you, right? You sort of lose a factor of Q each time. And so fundamentally for all these problems, it seems that what you need is for there to be a range that's linear between I and n. Like if I can say that if I can get stability for n bigger than like 1 million I, I'm happy. But if it's for n bigger than like I squared or something, then I'm sad, like that's not good enough. And there are actually homological stability theorems that have ranges like that. And those are like really good theorems, but they're not good enough to get bounds on point counting. I think it's kind of, I mean, I don't know what you think, Craig, but I feel like there's always been an open question. Is there really such a thing as a non-linear stable range? Or is it the case that in every case where we can prove a range that's worse than that, there really is a linear range that we haven't figured out how to prove? I don't know if you have thoughts on that question, but.
Yeah, I mean, Dan will be talking a little bit about the EN cellular way of describing these things. So when they arise like that, these guys come with a linear range. You can, so it's sort of automatic if it doesn't have too many cells, but then there's plenty of weird examples that aren't of that form.
Okay, that's a good answer because you'll never hear me say the words EN cellular because I don't know what that means. But we'll learn tomorrow.
Any more questions? Well, so you're going to see much more topology, I think, tomorrow. Because they will be talking about exactly these questions. And I encourage you all to come. So we have 2 intense days on this following this introduction by Jordan and this case that we discussed. This thanks.